Good evening. All right, so we're going to be going back to the textbook for this next topic of exponential growth functions. It's in chapter 13.1 of the textbook, the online textbook. I'm going to make my own video based on the textbook lesson, but I can't do the whole lesson. And you can always look at the Dr. Berger videos and Math on the Spot for this section. First, I would say that I skipped over the first part because it's a little basic and I want to get to the more bulky part. But if you look at page 635 in the textbook for this chapter, it goes a little bit into the graph of f of x is 2 to the x. It's an exponential graph. And also f of x is equal to 10 to the x power. I'll give a quick little graph of that on the next page. But this is what happens with the graphs. They'll be transformed, and we've done this before. When you have a horizontal shift and a vertical shift, a vertical compression, or a vertical stretch. And if you read this paragraph, you could see, I'm just going to highlight certain areas. So if we took the basic function of f of x, which is equal to 2 to the x, our base is 2. So for the b, that would be 2. And the only other thing that we would have in there is the variable of x, which is our domain value that changes. But when we put all these other shifts on it, it'll change the function of the graph, but it'll still have the parent function beneath it. So for example, the h value is what's going to shift it left and right. The k value is going to shift it up and down. And the a value is what's going to either compress it or stretch it vertically. And then they wrote that in here. So you can read this yourself from the chapter. I just wanted to highlight certain areas. And they use critical points. The first point is when x is 0, what happens with the range. But for all exponential functions, the parent functions, when x is 0, for example, if f of x here, this f of x, if f of x here was f of 0, let me fix that. Let's just change that and get rid of that and make that a 0, because that's what I meant to do. Let's say that was f of 0. Oops. Getting used to Microsoft Paint here because it's a long story. I'll tell you in class. But if that was f of 0, that would be 2 to the 0 power, and anything to the 0 power is 1. That's where this critical value comes from. And the other one is when you have the if your one value of the domain, it should be the value of b. And in our case, it would be 2. And you'll see with the transformations what changes. And all of these values that'll be a little bit difficult to get used to in the beginning become pretty easy. Let me see where my mouse is. Oh, there it's up there. So our h value is the shift left and right. Our a value is the compression or stretch. K value is the shift up and down. That's where the first point becomes. And then 1b becomes 1 plus the shift left and right, the stretch or compression times the value of the base plus the shift up and down. And the asymptote, which in our original function, let me just draw a quick one. If we have an original exponential function, they always have this form where they start out flat and they hit 0, 1, and then they continue and exponentially increase. That's a very bad drawing. But this portion of the graph is going to get closer and closer and closer to an asymptote. And for the parent function, like 2 to the x, it'll get closer and closer to y equals 0, or the x-axis. This is the x-axis. The parent function then becomes, now I gotta find where I am, then becomes y equals k, and that's the shift value. Because if you're shifting up and down from the y-axis, that value is going to make sure it's on that line. So this is where I'm going to spend most of the time explaining. The example says to state the domain and range of the given function, then identify the new values of the reference points and the asymptote. Use these values to graph the function, and we're going to do that. Just to review, the parent function that we're used to looking at usually has this form, where it's asymptotic to the x-axis, then it hits 0, 1, and then exponentially increases. This would be, I'll just name that f of x. So we're going to do a g of x, which has these parameters. Let's just identify some of the parameters here that we would see. This is our a value. This is our b value, the 10. X minus h, the 3 would be h, and the negative 5 would be k. So let's see what this guides us to do. Now, the domain of this function is still going to be all real numbers, because you're going to use all real numbers this way and all real numbers that way. So as, hold on one second, lost my mouse. As we start from negative infinity in the x, we will approach x, and then we will go all the way to positive infinity, non-inclusive. And then the range of our function will be anything less than, oh, I'm sorry, anything greater than, where am I? The negative 5, because negative 5 is the shift below. So I'll erase this and we'll do another function a little lower, but our asymptote is now going to be at negative 5, so our range is going to be anything above that. It is not equal to, because we'll never actually touch the asymptote. We'll approach it as we get closer to it. All right, now the a value, which we had before, we saw up top is 1.5 because it's stretched vertically by a factor of 1.5. The h value is 3. It shifted 3 units to the right. And our k value is negative because it shifts it down, negative 5. Okay, let me scroll down a bit. I lost my functions. There we go. Okay. The point 0, 1 becomes the value of h, and that's the x value, and a plus k becomes our y value. They already show that for us. So our h value is 3, and our y value is 1.5 minus 5, which becomes a negative 3.5. Let's plot that. 3, I have to scroll down a little more. 3 is about right here, and 3.5 goes about right there. So that is one of our critical points. 1 comma b becomes 1 plus the h value, and then a times b plus k becomes the y value. So 1 plus 3 is then 4. Sorry about the crookedness. And then 1.5 times 10 is 15 minus 5. What's 15 minus 5? That would be 10. So 410 would be another critical value. Here's 4. Here's 10. That's a very, very sharp increase because it's exponentially going up by tens. The asymptote becomes y equals k. Our asymptote was y equals negative 5 because that was our horizontal shift. So negative 5 is actually, this is negative 6, so I'm going to try my best to make this look nice. Oh, you know what? Let me use a line function. And let's use the thinnest one possible. I'll go with red. Let's see if I can do this. Oh, not too bad. There's my, that's the asymptote. Now this is going to be really difficult. I'm going to try to draw this graph. I'm going to use green. It's going to be way up here. Oh, I'm in the line function. Hold on. Okay. That's not going to look very nice. Well, that was my attempt. Let me try one more time from the left. Okay. This is much better. And then we're going to sharply turn up. And then it's going to go all the way through the point and continue on upward. And there's my thing. This is g of x, right? I think it was g of x. Let me scroll up. Yeah, q of x. I'm totally off. Q of x is this green function. The videos are already getting pretty long, so I'm not going to do the other parts of this, the your turns. You can do that on your own if you want. It's in the textbook. And we'll do a little more of this in class. So I hope you enjoyed my first video that I made in a while.